The warship Cerberus survived for nearly 7 decades as a static coastal breakwater before a massive storm triggered a sudden 6-foot structural collapse. The mechanism driving this catastrophic failure was not the wind tearing at the hull, it was the defining architectural feature of the vessel. The central armored breastwork citadel was designed to make the ship invincible in combat. Instead, it became the exact instrument of her destruction. To understand the failure sequence, one must examine the engineering logic of her construction. Launched in 1868, completed in 1870, and entering service in 1871, the vessel represented a radical departure from traditional naval design. She was the first iron-hulled British warship to be designed without masts and to be powered purely by steam. Removing the complex network of masts, sails, and rigging eliminated the severe top weight associated with the age of sail. It also cleared the decks. This provided an unobstructed field of fire for her massive rotating gun turrets. However, stripping the sails allowed naval architects to introduce a completely new distribution of mass. This is the breastwork principle. Instead of spreading a thin, protective layer of iron across the entire length of the hull, engineers concentrated the defense. They enclosed the vital boiler machinery, the steering gear, the ventilation shafts, and the lower turret mechanisms inside a heavily armored box situated directly amidships, protruding high above the waterline. That breastwork made her a floating fortress and set the trap. As a concept, the breastwork was brilliant. It wrapped the ship's vital systems in the thickest iron. But concentrating that armor high amidships pushed her center of gravity upward and packed the upper hull with unprecedented mass. Afloat, buoyancy could carry it. Once she stopped living as a ship, that same geometry would turn unforgiving. By 1924, naval technology had advanced rapidly, and the vessel was declared surplus and sold off. 2 years later, engineers made the calculated decision to scuttle her in 12 feet of water in Half Moon Bay. Her new operational mandate was to serve as a permanent breakwater shielding a local yacht club anchorage. Resting firmly on the seabed, the flooded lower hull effectively absorbed the kinetic energy of incoming waves. In that shallow water, the massive armored breastwork and the heavy gun turrets remained fully exposed above the surface. For decades, the Scuttled warship stood as an iron monument. To locals, it seemed dormant and permanent, its upper armor taking the coastal weather without complaint. In December 1993, that certainty snapped. A severe weather system struck the bay, driving gale-force winds and violent seas. Waves hammered the exposed iron, but they did not rip the hull open from the side. They drove the structure downward. Under repeated storm loading, the internal iron framing of the lower hull, weakened by decades of submersion, could no longer support the crushing mass above. The massive top weight of the central citadel overcame the failing supports, and the hull buckled beneath the waterline. In a matter of hours, the ship suffered a catastrophic downward collapse on the order of 2 meters. The upper deck plunged toward the seabed. The massive iron turrets tilted violently. The ship was no longer a dormant breakwater. It had instantly transformed into a dynamic, highly unstable structural hazard. In that instant, the geometry flipped. The breastwork and turrets were no longer inert armor. They became a vertical press, driving what was left of the hull into the sand. Investigators were left with one question. How did a warship endure for decades, only to start crushing itself in the shallows? Hundreds of tons of solid iron plate sit high above the waterline. Below this massive superstructure, a fragile, rotting foundation attempts to hold the entire payload in the air. The geometry trap is absolute. The ship features 2 enormous rotating gun installations. Each turret weighs somewhere in the vicinity of 175 tons. The central armored citadel concentrates this incredible mass directly amidships, but the structure supporting this immense weight is entirely compromised. The heavy upper plates were forged to deflect explosive shells. They retain their sheer density long after the operational life of the vessel has ended, but they are currently suspended over a void of deteriorating metal. The root of the structural crisis is electrochemical corrosion. Seawater acts as an electrolyte, and the iron breaks down cell by cell. The disparity in the decay rate is severe. The thick upper armor is exposed primarily to the air and occasional salt spray. It does not sit in continuous immersion, and so its corrosion rate is generally slower, though the splash and tidal zones can still be punishing. Therefore, the upper plates tend to show surface corrosion rather than the deep structural loss seen below the waterline. But the lower hull was originally constructed with much thinner iron, designed only to provide buoyancy and hydrodynamic efficiency. Decades of galvanic marine decay aggressively consume these submerged structural frames. Galvanic marine decay does not destroy a ship evenly. It prioritizes the most submerged, continuous metallic pathways. As the lower hull dissolves into the sea, it leaves behind a brittle, hollow shell. The salt water silently ate away the internal bulkheads, the transverse frames, and the critical deck beams. This creates a strict environmental denial regime. Traditional salvage would require passing heavy steel cables or slings beneath a strong, intact hull to lift it. Here, the degraded lower iron would be prone to tearing under concentrated loads, making a conventional lift extremely risky. Major patching and welding below the waterline would also be highly unreliable because so much base metal is heavily corroded. In practical terms, straightforward recovery by conventional methods is not feasible. As the lower hull loses mass, the upper armor retains its full 860 tons of dead weight. Every millimeter of iron lost from the lower frames increases the extreme vertical load on the remaining structure. The margin of safety steadily drops to zero. With recovery impossible and the hazard growing, the government intervened and declared the site a historic shipwreck. Authorities drew a protected perimeter, about 25 meters to either side of the center line and 5 meters beyond the bow and stern, keeping unauthorized vessels and recreational divers out. That same heritage status also blocked blunt solutions. Engineers could not simply dismantle the turrets or strip away armor, even as the structure continued to fail. This established an impossible operational standoff. Environmental denial prevented lifting the wreck or patching the lower hull. Jurisdictional denial prevented applying destructive salvage techniques to quickly eliminate the hazard. The massive warship was trapped in a state of terminal, unmanaged collapse. The engineering teams faced a blind crisis. They understood that the extreme top weight was crushing the rotting lower hull, but they could not physically enter the flooded, collapsed compartments to visually inspect the remaining thickness of the primary deck beams. Penetrating the confined spaces of the actively crushing hull to measure the iron was both a lethal hazard and a violation of the strict heritage perimeter. With traditional salvage blocked by law and physics, engineers needed a way to measure the invisible decay tearing the lower frames apart without touching the wreck. In silted, surging water, cameras could not answer what mattered, how fast the metal was dying. So the team turned to in situ corrosion mapping using tightly controlled, permitted spot readings and remote observation from the edge of the debris field. This electrochemical decay measurement system does not rely on optical cameras alone. Instead, it samples the corrosion potential of the metal in seawater. Divers place a calibrated reference electrode in the water and take readings with a high impedance meter, producing a diagnostic signal, an indicator of how active corrosion is at that spot, rather than a perfect standalone measure of structural strength. The survey team meticulously mapped these surface voltage potentials across the entire exterior of the wreck. The operation required divers to swim the perimeter of the vessel in the shallow surge zone, taking hundreds of individual voltage readings. The wave action in 12 feet of water constantly threatened to throw them against the jagged, deteriorating iron. Taking an accurate surface voltage potential requires maintaining a steady, fixed distance between the reference electrode and the hull. If the diver drifts in the current, the voltage gradient shifts and the resulting mathematical data becomes completely useless. The dive teams had to execute perfect station keeping to capture pure numbers. By comparing the data from the upper armor with the readings from the submerged lower hull, engineers isolated the exact zones where electrolytic iron corrosion was destroying the structural integrity of the ship. The engineers spent weeks compiling this hard-won data. They cross-referenced the voltage potentials with historical blueprints. This allowed them to estimate remaining metal condition in key structural areas without major cutting into the hull. The math revealed a terrifying baseline. By analyzing the voltage gradients, the team calculated the precise speed of the destruction. The ship was losing critical mass at an alarming rate. The electrochemical measurements translated the invisible structural rot into a concrete mechanical equation. The hull was experiencing an estimated gradual subsidence measured in fractions of an inch. Since the initial catastrophic collapse of 1993, gravity and ongoing corrosion had continued to drive the heavy upper decks downward in small cumulative steps. Every single reading fed into a master corrosion model. This mathematical model eliminated all the historical guesswork. It proved that the central armored citadel was completely unsupported in several critical sectors. The lower transverse frames had steadily vanished into the sea. The remaining structural iron was so heavily compromised that it possessed almost zero tensile strength. The in situ corrosion mapping proved that the massive visible upper armor was merely resting on a fragile, hollow lattice of failing metal. The survey was an absolute technical success. The engineers had successfully visualized the microscopic decay of the internal frames strictly from the outside. They possessed a perfect digital representation of the degradation. But this achievement hit a hard physical limit. The sensors could perfectly read the decay, but they could not physically reinforce the missing iron. Knowing the exact surface voltage potential of the rotting hull did not add a single ounce of steel back to the collapsing deck beams. The data answered exactly how fast the ship was dying, but it raised a terrifying new structural deadline. Losing 5/8 of an inch of vertical elevation every year is a mathematical death sentence for a heavy structural span. In the early 2000s, engineers completed comprehensive geotechnical and structural assessments of the vessel. The survey findings delivered a stark warning. Key interior supports were approaching, or had already crossed, the threshold needed to sustain the massive vertical loads. The central paradox of the shipwreck is a mechanism known as top-weight subsidence. In traditional naval architecture, a ship is designed to balance immense loads. Structural weight transfers evenly outward and downward through sturdy internal deck beams, vertical bulkheads, and heavy transverse frames directly into the lower hull. But decades of submersion eradicated that vital internal support network. Gravity is a relentless, continuous force. The heavy upper decks, once supported by thick, rigid iron pillars, were now spanning large, empty, flooded voids. As the primary lower supports rusted away into the seawater, the immense downward force of the upper armor simply forced the entire horizontal plane of the upper deck to sink. The upper mass was actively crushing the brittle, weakened iron beneath it. The ship was literally collapsing under its own defensive strength. The 2003 structural assessment proved that this localized iron loss had reached a critical and irreversible threshold. The survey data mapped by the remote instruments confirmed that the horizontal interior deck beams beneath the main guns were heavily compromised. Directly above them sat the fore and aft rotating gun turrets, immense masses concentrated on the weakest span. With the beams dissolving, that load had nowhere safe to go. The structure was already at its ultimate limit. The geotechnical conclusion delivered to the government was absolute. A catastrophic collapse of the main deck underneath the heavy turrets was entirely imminent. If those deck beams failed, the massive iron turrets would punch straight down through the center of the ship, obliterating what was left of the lower hull and destroying the historical integrity of the entire site. The surveys had done their job. They proved the timetable of failure. But the spaces directly beneath the turrets were unreachable, and the metal there was too far gone to accept any conventional fix. The degradation of the iron was so severe that commercial dive teams could not safely enter the flooded lower hull to visually inspect or measure the remaining internal deck beams directly. The risk of the heavy deck instantly pancaking downward onto the divers was too great. Even if an engineering team could magically bypass the hazardous entry and reach the flooded internal void, the material physics offered no solution. There was absolutely no solid metal left to act as a foundation. They could not install temporary hydraulic jacks. They could not insert heavy steel reinforcement columns. You cannot weld new structural braces to a floor composed of disintegrating iron oxide. The interior environment strictly prohibited any physical intervention to save the crumbling deck beams. The entire vessel was completely locked in a terminal, unyielding standoff. The mathematical survey data perfectly proved the imminent failure of the heavily loaded main deck, but the physical reality of the site completely barred any conventional internal reinforcement. The heavy top-weight subsidence was mathematically guaranteed to destroy the remaining ship. If the entire lower hull could not be lifted or recovered and the crumbling interior decks could not be braced from within, How could the impending total collapse possibly be stopped? To save the historic shipwreck from destroying itself, the government had to grant permission to dismantle a vital piece of it. The trade-off knife cut straight through the strict preservation laws. The choice was binary: either sacrifice a fraction of the original armament or lose the entire vessel to the sea. The heavily corroded main deck was mathematically guaranteed to fail. The only engineering solution left was to fundamentally alter the physical mass resting on those failing beams. They could not reinforce the rotting lower hull, so they had to reduce the crushing payload pressing down upon it. In 2005, the engineering standoff forced a critical decision. The authorities managing the protected heritage site issued a rare, conditionally permitted intervention. If they adhered strictly to the absolute prohibition against touching the wreck, a gravity-induced collapse would obliterate the surviving architecture. To avert total destruction, engineers proposed a highly specific operation known as a surgical lift. This was not bulk salvage, it was controlled stress relief. Remove just enough mass from exactly the right place as to slow the collapse without jolting the wreck. The math did not ask for heroics, it asked for subtraction, and the turrets offered the cleanest target. The most accessible and mathematically viable targets for extraction were the primary weapons of the warship. Housed inside the two massive rotating turrets were 4 original muzzle-loading guns. Each individual weapon weighed about 16 to 18 tons, depending on how it is recorded. Removing these specific components would instantly relieve roughly 64 to 72 tons of concentrated downward force from the 2 most vulnerable sections of the upper deck. Operating under the strict parameters of the conditional heritage permit, the salvage contractors mobilized a heavy lifting barge. The crane vessel maneuvered to the absolute boundary of the site. Operating under incredibly tight tolerances, the crane operators had to reach out across the submerged debris field. They could not drop anchor near the fragile hull or allow the massive steel lifting rigging to swing against the unstable historic armor. The salvage team had to extract the heavy iron cylinders straight up through the narrow confines of the turrets. There was absolutely no room for error. If a suspended 18-ton gun swung like a pendulum and struck the inside of the rusted turret wall, the kinetic impact could instantly trigger the exact structural failure they were trying to prevent. One by one, the salvage team rigged the 4 massive weapons. They successfully hoisted the original guns clear of the internal carriages, pulling them high into the air and away from the dying ship. The extraction was flawlessly executed. Exactly 72 tons of dead weight were successfully subtracted from the mechanical equation that was actively crushing the ship. The targeted stress relief immediately reduced the sheer force acting on the brittle interior deck beams. This precise reduction successfully averted the immediate catastrophic failure predicted by the prior geotechnical survey. The heavily loaded turrets would not punch through the floor today. The permit solved only the immediate spike in risk. The guns were gone, but the empty armored turrets and the breastwork still bore down on a lower hull that corrosion continued to hollow out. The lift had bought time, not stability, and engineers now had to shift the remaining load onto something that would not rot away. They found the final structural solution in the few elements that still retained real strength. Reports noted that the armor belt remained comparatively intact even as the thinner, unarmored structure below the waterline continued to vanish. Instead of trying to rebuild a hollowed ship from the inside, engineers focused on shifting loads away from failing frames and onto something the seabed could carry. The preferred stabilization concept was blunt, practical, and scalable. Build a low protective wall around the wreck's base, then fill the interior with dredged sand so the turrets and surviving superstructure would be supported by the ground beneath, not by rotting ironwork. But even a successful stabilization would establish a hard limit. A full restoration or complete recovery would remain unlikely without a major, purpose-built project and sustained funding. The lower, unarmored iron has already suffered severe loss, and ongoing corrosion is expected to continue. The goal, therefore, is not a triumphant resurrection. It is risk reduction, controlled change, and preserving as much of the surviving structure as realistically possible in situ. The vessel exists today not as a fully recovered maritime artifact, but as a heavily monitored, strictly managed ruin. Authorities maintain the rigid legal exclusion zone, and continue to actively scan the structural perimeter. They treat the shipwreck as a permanent, active fixture on the environmental hazard watch list. The lower hull has been freely surrendered to the ocean, intentionally sacrificed to ensure the long-term survival of the upper decks. The great warship remains indefinitely trapped in the shallows of the bay. It is locked in a final, unyielding standoff between massive 19th century armor and relentless marine physics, permanently frozen in a state of monitored decay.